Yo, let's get back at it. All right, here we go. We are on question 13. All right, so what do we got going on for this guy? Oh, you gotta get that pen working. There we go. All right, 13. All right, so it says let f be a function defined for all real numbers x if f prime of x is equal to the absolute value of 4 minus x squared over x minus 2, then f is decreasing on. So then f is decreasing on. And you got to figure that out. All right, so bread and butter here, people. F is decreasing when f prime is negative, right? Basic concept. So maybe first find out when f prime is 0 or undefined. So you have a fraction here. So a fraction is 0 only when the numerator is 0. So you can set the 4 minus x squared equal to 0, right? Solve this pretty quickly, however you want to do it, or just see it. X equals plus or minus 2. So what I'm going to do now is I'm going to make a sign line, label it f prime. I'm going to put negative 2 on here, put 2 on here. And let's see. So obviously the top is 0 when x is 2, but notice that makes the bottom undefined. So it makes the bottom 0, which makes the fraction undefined. So that's going to make it undefined, but it's still good. It's still a point of interest, right? Still a critical point. And the top is 0 when x is negative 2 and the bottom is not. So that means a fraction 0. And then you just test, right? So what are you going to test? Well, maybe I'll test 0. If I test 0, right, the top is positive. In fact, the top will always be positive because there's an absolute value there. And the bottom, 0 minus 2, is negative, right? So positive divided by negative is negative, right? If I test 5, again, top is positive. 5 minus 2, that's positive. You get positive. And if I test, say, negative 5, top's still going to be positive. The bottom would be negative 5 minus 2. So that's going to be negative. So positive over negative is negative, right? So we got that going on. And so now we got to figure out where f is decreasing. Well, f is going to be decreasing when the derivative is negative, right? So that's going to be negative infinity to negative 2. And you can union that with 2 to 2. Now, when you're talking about decreasing, you actually can include endpoints here as long as they're in the domain of the function, and this would be. So you really can spruce this and say that it's decreasing from negative infinity to 2. All right, and if we look at the choices, that looks like that's going to be choice A. All right, so choice A it is. All righty. All right, remember, you can include endpoints when stating intervals of increasing and decreasing. You don't do that with concavity. You do with increasing and decreasing. All right, 14. It says, let f be a differentiable function such that, this is 14, such that f of 3 equals 2 and f prime of 3 equals 5. And then it says if the tangent line to the graph of f at x equals 3 is used to find an approximation. All right, so tangent line to approximate, that's a linearization. So you want the linearization at x equals 3. All right, and then it says if you use that, then approximation for f at 3 would be what? All right, so let's think about the information they give you. When you see f of 3 equals 2, you should think, oh, they're giving me a point. That's 3 comma 2. Easy breezy. All right, when you see f prime of 3 equals 5, you should think, oh, they're giving me a slope. All right, so m tan is 5. So remember, linearization's point slope formula, right? Write the equation of a tangent line. So if I do that, I'm going to get y minus 2 equals 5 times x minus 3. So there's the equation of my tangent line, right? So now to make it a linearization, it's pretty simple. Just solve for y and change the y to fancy notation L of x. So I would add 2 to both sides, change the y to L of x, and basically I'm going to get that. So that is my linearization. Now remember what a linearization is. It's an approximation function. L of x approximates f of x. So in a crude little world, if this is my curve f of x, not necessarily in this problem, right? Looks like that. Then this would be L of x because it's just a tangent line. Looks like that. We're using this to approximate f of x. And at first glance, you're like, that's horrendous. But remember, it's only good for values of x that are close to the point of tangency. Okay? So now the question here said, if the tangent line to the graph of f at x equals 3 is used to find approximation of to a 0. All right, so that's a pretty cool question. I didn't read that in the beginning, but I read it now. All right, so you're like, well, how do I do that? Well, you're using L of x to find the 0. So instead of using f of x, you're using L of x. How do you find the 0 of a function? You set the function equal to 0. So basically, I'm going to set this function, L of x, equal to 0 and solve however we want to solve it. So maybe I'll distribute 5x minus 15 plus 2 equals 0. That's negative 13 added over 5x equals positive 13. X equals 13 over 5. So that's when my tangent line would be 0, and we're using that to approximate when the function would be 0. Okay? So that is going to be, 13 over 5. What is that? That's going to be 2 3/5, right? Or 2.6. Yes, we have to be able to do that without a calculator. So that's going to be choice C. All right, 13 over 5 is 2.6. Good? That was a festive little question. I like that one. All right, rocking and rolling. Let's go to question 15. This is 15, okay? It says the graph of f of the function, f is shown in the figure below, which of the following statements about f is true. So it says a couple of things here. I should probably write them all out. This would have been better if I snipped this, but I didn't, so I'll write it out. All right, so what do we got going on? Def, pay attention. Come on. Pick your head up, bud. Killing me. All right, so we go. Limit of f of x as x goes to a, this is choice A, is equal to the limit of f of x as x goes to b. So we want to know, is this true or is this false? So limit of f of x as x goes to a, so as x goes to a from both sides, our functional values, our little buggies, are approaching 2. So that would be 2. Limit of f x goes to b, that does not exist, right? Because as x goes to b from the right, our little buggy is approaching 1. But as x goes to b from the left, our corresponding functional values are getting close to 2. So this does not exist. So 2 does not equal does not exist. So it ain't choice A. You can cross that out. All right, so let's go to choice B. So choice B says the limit of f of x. Hopefully, as I do more of these, my handwriting and flow will get better. Limit of f of x goes to a is 2. That is correct, right? So again, as x goes to a from the left, your corresponding functional values are getting close to 2. And as x goes to a from the right, your corresponding functional values are getting close to 2. So that means your two-sided limit is 2. So that is kosher. All right. So that is true, actually, and that's what we had to find. So there's your answer. So 15 is B. All right. We don't have to check the others out. And I think I basically addressed C, D, and E when I explained this. So we're good to go. All right, let's rock and roll. Let's go into question 16. If you hear any noise in the background, my dog is about to go bananas. All right, so 16. Says the area of the region enclosed by the graph of. So remember, this is a non-calc question. So you got y equals x squared plus 1, and you got y equals 5. And you have to find the area of the region enclosed. So yeah, you have to be able to sketch this without a calculator. So x squared plus 1 is just a parabola shifted up 1. Right, where this would be 1 right there. So that's pretty basic. And y equals 5, that's just a constant function. That's a horizontal line. That's going to be y equals 5. Okay, so we're trying to find the area of the region now. All right, so whoa, getting out of control with these colors here. Highlighter. Do I want highlighter? Thin highlighter? Oh, look at this. All right, so there's the area of the region enclosed by those graphs. So let's go back to pen. How do we do it? All right. How do you find the area of a region? It's just basically the integral of the top minus the bottom if you're going to do it with respect to x. And it's the integral of right minus left if you're going to do it with respect to y. So this would be pretty easy to do with respect to x. But you do have to figure out what these x values are. So how do I do that? Well, you got to figure out when x squared plus 1, that's the graph of this here, right, is equal to 5. Basically set them equal. Subtract the 1, and you get plus or minus 2. So that's negative 2, and that's 2. All right, so if I'm setting this up now, let's go back to my black pen. You'd have the integral from negative 2 to 2 of the top, which is 5, minus the bottom, which is x squared plus 1. What do we have to be careful about? Matt, what do you think? Yes, Matt. Good job. Parentheses. You got to use parentheses there. All right. So here we go. That's what we got. And we can spruce this, and so I will. There's a couple things we can do here. All right, Duff, put your hand down. All right, so here we go. So you can have 5 minus 1, so that's going to be 4 minus x squared dx. So that's what we want to integrate. And we can rock and roll with this, but remember, this is a non-calculator question, and time is definitely a factor on this exam that hopefully you'll be taking. So you're like, well, how can I make this more efficient? What can I do? Well, both of these curves are even. In other words, they're symmetric to the y-axis here. So what you could do instead is you can just find the area of that region, right? And then just do what with it? Liam? Very good. Multiply by 2. Good job, Liam. So here we go. So it would be 2 integral from 0 to 2 of 4 minus x squared dx. And obviously we wanted to do that because if 0 could be one of our limits, and that's obviously a home run. So here we go. Let's find the antiderivative. So those people in the background, just ignore them. All right, so we have 4x minus power rule here, 1/3 x cubed, integral of the difference of the integrals. Evaluate that from 0 to 2. Don't forget your little 2 out in front. And so now we're going to have 2 times, first chuck in the 2, 4 times 2 minus 1/3 times 2 cubed. That's my f of b, minus my f of a, which the whole point of doing this is 0 minus 0 is 0. So I'm being a little lazy there by writing it that way, but that's what happens. So now you're going to get 2 times, this would be 8 minus 8/3. I'd rather think of 8/3 as Brockbank, very good, 24/3. And so 24 minus 8 is 16/3. So you're going to get 2 times 16/3, which last time I checked is 32/3. All done without the use of a calculator. So hopefully that's an answer. If it's not, life's not going to be fun. So 16 is an answer, has an answer. It's D, 32/3. All right, and that's it. So pretty in-depth multiple choice question, right? You can see you got to move when you do these problems. All right, let's hit up question 17. Question 17 says, you have x squared plus y squared equals 25. It says, what is the value of this weird looking symbol d2y dx2, otherwise known as the second derivative of y with respect to x at the point? Didn't have it this notation way, but I'm going to write it. Evaluated at 4,3. So how do you do it? Well, obviously, you got to get the second derivative, and then you just chuck in the point 4,3. So this should be pretty basic. So how do we find the derivative here? Do not try and solve for y explicitly. Do it implicitly. What does that mean? That means you're taking the derivative of the left side with respect to x, treating y as a function of x, and you're taking the derivative of the right side with respect to x. What does that mean? Well, let's just do it. So here we go. So the derivative of a sum is the sum of the derivatives. So the derivative of x squared is 2x, right? 2x to the 1. Easy breezy. What's the derivative of y squared? If I said what's the derivative of y squared with respect to y, you would tell me 2y, you'd call it a day. But I'm not asking that. I'm saying what's the derivative of y squared with respect to x, where y is a function of x. In other words, y is stuff. So it's a composition. So you have to use the chain rule. So it's going to be 2 stuff to the 1 times the derivative of stuff. So in other words, times the derivative of y. So times dy dx. All right, equals the derivative of 25, which is 0. Right? If I'm doing this, I notice that I can divide both sides of this equation by 2. Yes, including the 0. 0 divided by 2 is 0. So that's a quick little spruceage maneuver. And now I get x plus 2y dy dx equals 0. So I got to get dy dx before I get the second derivative of y with respect to x. There's no 2 there. So simple enough. Dy dx equals, subtract the x over, divide by y, and that is my first derivative. So what do I do now? You do it again, all right? So you're going to take the derivative of this side with respect to x, and you're going to take the derivative of this side with respect to x, treating y as a function of x. All right, so it should be easy breezy. So what's the derivative of the derivative? Yes, you guessed it, the second derivative. All right, so that's easy. How do I take the derivative of the right side? What do I have? I have a quotient. So what do I need to use? I have to use the quotient rule. So this little negative can sometimes cause people issues like, where do you put it? Do you put it in the bottom? Do you put it to the side? Do you put it to the top? If it's me, I'm just including it as a part of my top. So when I go to apply the quotient rule, the way I have it remembered, right, is bottom times the derivative of the top. So bottom times the derivative of the top, all right, minus the top, right, times the derivative of the bottom. Now the derivative of y with respect to x is 1 dy dx. And then all over, right, don't forget that the bottom squared. All right, so that's what we get. And you're like, well, this is pretty ugly. You have a second derivative in terms of a first derivative. If only we knew what you were, right, that'd be great because we could just throw you in and you're like, oh, but we do. Dy dx is just negative x over y. So that can get substituted in right there. So let's do this and let's make sure I don't make any mistakes. All right, so what do we got? We got negative y and now minus minus, right? That's going to be plus, but then there's another minus there. So that's minus x times x is x squared over y, and then all of this over y. Now, quite honestly, you don't really necessarily need to spruce this. And let's see, how can I extend this? Full screen. Oh, beautiful. Extend page, all right? So you don't really need to spruce this. You literally could just start chucking the point in right now. And it's probably what I would do. But just for note flow and flavor, and maybe it's a different question where you need to find the actual algebraic expression and not evaluate it at a point, let's figure out how we would simplify this. So to simplify this, you're like, well, what's the deal here? What's making this annoying? Why is this an ugly fraction? Because you have a fraction divided by a fraction, right? So there's a fraction sandwich, and no one likes fraction sandwiches. So you're like, oh, how do I get rid of divided by in math? Oh, look at that. It's pretty simple. You just multiply by that thing that's causing the issue. And you got to remember to multiply the entire top of the fraction by it. So then you have to multiply the entire bottom of the fraction by it. So then you're really multiplying by 1, so you're not really doing anything. So then if I distributed that, I'd get negative y squared. Here, the y's cancel when I distribute, so I get minus x squared. And on the bottom, I get y cubed. All right, and that's like a nice clean looking version. If I wanted to go even more bananas, I can pull the negative out completely, because this could be a choice if it was just find the second derivative, and maybe even write something like x squared plus y squared over y cubed, and you end up getting that. All right, so that's pretty cool. If I wanted to be even more bananas, right, you're like, well, wait a minute. X squared plus y squared, I kind of remember that equaling something, right? So if you look up here, you're like, oh, look at that. X squared plus y squared is 25. So if you wanted to go ballistic, you can chuck a 25 in for that. And now you got this fancy, spruced up second derivative. Now, at the end of the day, you have to evaluate it at the point 4, 3. All right, so at the point 4, 3. So there's my x, there's my y. So if I'm doing that right now, I'm going to get negative 25 over. It looks like I'm only going to chuck the y in the way I did it this way in there. So y cubed is going to be 3 cubed, which is 27. So I end up getting negative 25 over 27, which is choice A. All right. I'm thinking most of you probably wouldn't have done this craziness with the substituting in right here. And that's totally fine. You literally right here could have chucked in 4 where you saw the x, 3 where you saw the y, and did the arithmetic. Try doing it on your own. You'll get the same answer. All right. But I just wanted to show you some magic that would have happened if it was a different question. All right. So that's that. So all right, we're at 18 now. 18. So we got the integral from 0 to pi over 4 of e to the tangent x divided by cosine x. Cosine squared x. Look at that. Cosine squared x dx. You look at that and you're like, this is a non-calculated question. Are you out of your mind? Really? I'm supposed to do this? And yes, you are. So, let's do some things here, right? What's the story, right? Well, I've told you before, if you're going to integrate a function that's got an exponential, then typically you let u equal the exponent, right? So in other words, your Jedi training has led you to believe that u should equal tan x. And you're like, all right, well then du would be derivative of tan x, supposed to memorize that, secant squared x dx. And at first glance, that might be like scary because you don't see secant squared x dx. But then you're like, wait a minute. What is secant squared x dx, right? It's 1 over cosine squared x. So again, just for note flow here, if I rewrote this, I could write this as e to the tan x times 1 over cosine squared x dx, right? These are equivalent. You should all agree to that? Do you agree? Good. All right. So now, well, what is this? Well, this right here is secant squared x. So if I wanted to take it a step further, just to really drive home that idea, rewriting the original problem would be rewritten this way. And yes, that is my boxer beating the crud out of my Shih Tzu right now. I don't know if you hear that or not. Anyway, all right, so here we go. So yeah, we rewrote the problem. We see it. Great. So think about it now. What do you have? Let's bust up some colors here. This right here is just not u, it's e to the u, right? And then this right here, if you hear that fighting upstairs, that is my girlfriend and the daughter. They're fighting about what they should be doing during the day. She stays up in the room too much. This is du. So you have the integral of e to the u du. All right, so we're good to go. So now what else do we have to do though, right? So if we're going to change our variable to u, not that you have to do this, but typically we do it. I like to do it. Is you're going to change your variable to u, you should change your what? Jess, good job. Change your limits. All right. So how do we do that? So I like to say, hey, when x is pi over 4, u would be the tangent of pi over 4. Tangent of pi over 4. Yes, you have that memorized. It's 1. All right. And when x equals 0, u is equal to tangent of 0. Tangent goes through the origin. That's just 0. So those are much nicer looking limits than what we saw up front. So now when I rewrite this, I have the integral from new limits 0 to 1, and I purposely find the top limit over the bottom limit of my work so that when I see this is exactly how they appear on my integral. I know that sounds silly, but when you're stressed out sometimes, the lower number is always on the bottom, and that might cause you to make an error. And then we have e to the u du.
Oh, yeah, that's how he gets into his Chromebook.
So when we integrate this now, a function whose derivative is e to the u is just e to the u, easiest one in America. And then you're going to evaluate that from 0 to 1. And so that's going to be e to the 1 minus e to the 0. E to the 1 is e to the 0 is 1, and you're done. So what looked like was going to be pretty bananas actually wasn't too bad, and that's choice C. I always look at the choices because I'm like worried I'm going to do the problem and it's not going to be there. I'm sure that's going to happen. All right, 19. All right, what do we got going on 19? Oh, we got absolute value. All right, absolute values are our favorite. All right, so this is actually pretty neat. So for 19, we have f of x equals the ln of the absolute value of x squared minus 1, and you have to find f prime of x, okay? So this goes to the fact that you have some rules memorized, and I don't want to go too much into it, but the derivative of ln of x is simply going to be 1 over x. But the derivative of ln of absolute value of x, believe it or not, is still 1 over x. And you know what? I said I wasn't going to show you, but let's just show you why that is real quick. So absolute value functions, 87.6% of the time, if you're going to do any sort of analysis on them, you want to write them as piecewise functions. So this guy written as a piecewise function would be the ln of x or the ln of negative x, right? We kind of know the deal there. Absolute value of x is either x or negative x, depending on whether x is positive or negative. So think about this now, and I'm kind of making up my notation here. If I take the derivative of ln of x, that we know is 1 over x. Well, what if I take the derivative of ln of negative x? Well, that would be 1 over negative x times negative 1, right? 1 over stuff times root of the stuff, and that's just 1 over x. And so, I get it. So long story short, when you go to take the derivative of ln of absolute value stuff, believe it or not, you can kind of ignore the absolute value. It's not going to come into play. So you're literally just going to get 1 over stuff times the derivative of stuff. So 2x over x squared minus 1. So now if you look at the choices, 3 of the choices have absolute value in it. Clearly, those are the distractors. Those are for the people that don't pay attention in class, all right? Because you think, there's got to be an absolute value in the answer. There's an absolute value in the choice. But that's not the case, right? Because the answer is D. So you got to be careful there, all right? Any questions? I didn't think so. All right, so here we go. So let's go on. I got to do a little scrollage here. Let's go on to question 20. All right, so question 20. All right, the average value of cosine x on the interval -3 to 5. So average value cosine x, integral -3 to 5. These are what I see as I read the problem. I don't see any of the other stuff, right? So you're like, oh, average value. I have a formula for the average value of a function, right? So the average value of a function is 1 over b minus a, integral a to b of the function. So in this case, it'd be 1 over b minus a, integral a to b of the function. I mean, that is just straight up how you find average value. So you're like, all right, this is going to be 1 over 8. This is going to be integral from -3 to 5 of this. So we should be able to do this, again, without a calculator. So give me a function whose derivative is cosine x. And the answer would be sine x. All right, and then evaluate it from -3 to 5. And you're like, all right, fundamental theorem of calculus. First, I have to chuck in the 5. So I pulled that 1/8 out. So sine of 5 minus, then I have to chuck in the -3. And I end up getting that. And now I look at all the choices, and all of the choices are written kind of like a fraction, right? So I'll write this as a fraction, sine of 5 minus sine of -3 all over 8, right? It's another way to write it. So I'm looking at my choices here, and there are two choices that have a denominator of 8. So if you have half a clue, it's a 50-50 shot, but the problem is you don't see this exactly. All right, so what do you see? You see sine of 5 minus sine of 3 over 8. That's choice A. And then for choice E, you see sine of 3 plus sine of 5 over 8. And you're like, I don't know what the deal is. I did all this right. What the heck is going on? So these annoying little people here that made this question are testing you on, do you know what to do with that? So what do I do with that? Sine, people, is an odd function. That means it's symmetric to the origin. So it's not the greatest graph, but if I kind of graph this like that and did something like that, if I was to take this thing, let's see if I can do this. This wasn't the greatest. Where's my little arrow? If I was to take this, oh, look at this, and flip it, right, it looks exactly the same. If you can do that to a graph, if you can rotate it 180 degrees and it looks exactly the same, it looks like it hasn't moved, that means that it's symmetric to the origin. All right, that means that the sign of a negative value is the same as the sign of a positive value. All right, so specifically, it means, algebraically, it means this. It means that if function's odd, it means that f of negative x equals negative f of x. That's what it means. So sine is odd. It's an odd function. So that means that sine of negative x equals negative sine of x. So in this case, sine of -3, let me go back to my thin here pen, right? The sine of -3 would equal negative sine of 3. And then that ends up being plus. And so you end up getting pluses here. So that, addition is commutative. That's basically choice E. All right. So 20 is choice E. So it was using the fact that F is odd. All right. You should also know what F is even, but I don't want these videos to be super long. So I'm going to move on until we just approach that topic. Or you can ask me about it. Just think about it and mentally I'll know that you have that question. All right, here we go. 21. We have the limit as x goes to 1 of x over ln of x, right? So what's the story with that? Well, directly substitute. You should always directly substitute first when you're doing a limit problem. The problem is if you did that, you'd get 1 over ln of 1, right, which is 1 over 0, which is not defined, okay? So now that means the limit does not exist. So you know for a fact that the limit is not going to exist. And if that's a choice, then rock and roll, go get them. Okay. Pick it. Okay. Sometimes though, you'll have choices like infinity or negative infinity, and you'll have to further classify or explain why it's not defined. So there's a couple ways that you can do this. Back in the day when we weren't doing L'Hopital's rule, you can think about this. So in other words, the ln of x graph looks like this. I've told you before you should know what that looks like. It'll help you in limit questions, right? Basic log graph, asymptote of the y-axis, right? Y equals ln of x. So now think about this, right? As x, this is 1, by the way, right? Every log graph goes through 1, 0. As x goes to 1 from the right, ln of x is going to 0 from the positive side. As x goes to 0 from the left, ln of x is going to 0 from the negative side. So depending on what side you go from, this could be a positive or a negative tiny number down there, which means you're going to get opposite infinities, which is probably why they just gave you that choice. But, and by the way, the answer is choice C, but what if this was the problem? What if it was that? Right? So the top, x goes to 1, just directly substitute. The bottom, you're like, oh, ln of 1. You're like, right? Number over 0. We talked about this. What do? We use tiny on one-sided limits. So I would put tiny down here, but you have to decide, is it positive or negative tiny? As x goes to 1 from the right, ln of x is going to 0 from the right, so it would be positive tiny. So this limit here would be positive infinity. That's the way to do it without L'Hopital's rule, right? We'll do L'Hopital's rule on another problem. We're going to keep rocking and rolling here. All right, so let's go to question 22. All right, 22. It says, let me just pull it up here. It's a little bit annoying. All right, we got it. All right, it says, what are the values of x which the function is defined by? So you got, oh, we're in red now. So we're going red. Let's just go with it. Going red. All right, so we got f of x equals x squared minus 3 times e to the negative x. And you want to know it's increasing. So when is f increasing? So you know the deal. F is increasing when? Yes, you guessed it. F prime is positive. So you got to get f prime. All right. So f prime, right? What do you have here? You have a product. So how do you take the derivative of a product? It's going to be, that's my first. That's my second. I like to remember it as first times root of the second plus second times root of the first. You might have a different way of remembering it. Good for you. All right, so here we go. So we have first, I went to black, sorry. All right, that's the first, don't mutilate it, times the derivative of the second. Second is a composition, it's e to stuff. The derivative of e to stuff is e to stuff times the derivative of stuff. The derivative of negative x is going to be negative 1. Plus the second times the derivative of the first. The first is a difference, derivative of difference of derivatives. So that would be 2x minus 0 or just 2x. So that's what we get. So now I got to see where f prime is positive, right? So it means first I'm going to have to figure out when it's equal to 0. So what can I do here? Well, it looks like I can pull out an e to the negative x. And then I have a negative x squared minus 3, right? And then a plus 2x, and then set that equal to 0. So now obviously this, I want to distribute the negative and then rearrange these terms. So if I distribute the negative, I get negative x squared plus 2x plus 3. I kind of did two things at once there. I probably should have pulled out a negative e to the negative 2x, which I'm going to do now. I'll pull out that negative because you like to work with, if you're going to factor, you'd prefer your square term to be positive. It doesn't have to be, but it just seems like that's the way we learn, so it's easy to remember it that way. All right, so what's the deal? Well, I'm going to try and factor this. So if I factor this, it looks like x minus 3, x plus 1, right? Negative 3 times 1, negative 3. Outer, inner, add to negative 2x is going to work here. So now what's the story? I have a product equal to 0. So either this factor is 0, this factor is 0, that factor is 0, right? Those would make that thing 0. So let's go full screen here. Let's scroll down. So you're like, all right, so what value of x makes this factor 0? Pretty obvious, x equals 3. What value of x makes this factor 0? Pretty obvious, x equals negative 1. Yeah, what about this? This will never be 0, right? This is like negative 1 over e to the x, right? And so that is positive, and with a negative in front, it means that stuff in front will always be negative, no matter what x is. Okay, negative exponents don't mean negative numbers. Remember, they mean basically that, 1 over in that case. All right, so what's the story? Well, I got to make my sign line. I'll make it over here. Label this bad boy f prime. Put negative 1 and 3 on here. 0's above. And now test. So if I test 0, which would be in here, That's negative. That's positive. Negative times positive is negative times negative is positive, right? So I have odd multiplicity, so they should switch, but we'll test anyway. So if I test 5, again, this is always negative, positive, positive, so that's going to be negative. And then if I test negative 5, both of these would be negative. Negative times negative is positive times negative, negative. So I get that. So I now know where the graph of f is increasing and decreasing. I just burped, excuse me. And so the question was, where is the function increasing? So that would be on this interval. So f is increasing on -1 to 3, which I could close bracket, by the way, and that will be because f prime greater than 0 on that interval. So that is choice D, and they wrote it as inequality, right? So instead of doing the interval notation, they did -1, and they actually left it open, less than x, less than 3. Okay? Cool beans? All right. Moving on. We're almost there. This takes a little bit of time, I'm not going to lie. All right. So what do we got? We got 23. So it says, if the region enclosed by the y-axis, the line y equals 2 and the curve y equals x is revolved about the y-axis, then the volume of the solid generated is. All right. So again, it's a non-calc question. So let's kind of sketch this. It's going to be rough to do on this, but I'll give it a go. Get rid of you. Well, get rid of all of you. Let's try that again. Can actually pull up Wolfram. Just a moment to do that. Let's see if we can just do the quick little sketch. So we go wet and wet. All right. So what do we got? We got y equals radical x. So that looks like that. We got y equals 2, which looks like that. And we got the y-axis, which is that there. So the region that we're revolving, we'll go a little highlighter action here, is this, right? And we want to revolve this region around the y-axis, right? Is that what it said? Y-axis, which means if you're revolving around y, you have to integrate with respect to y. So everyone needs to be in terms of y. And right now I have y equals radical x, so I really want to get that in terms of y. So solve for x. So square both sides, and you end up getting that for this curve right here. So that's good stuff. Okay? So now, not that it's 100% necessary to draw these pictures, and we've talked about this in the past, but right, if you're revolving, you're going to make a solid. You have to decide, is it discs or is it washers, right? And this is going to be discs, and that's because there is no space between the area you're revolving and the axis you're revolving around. So now if I was to do this, that wasn't the greatest. I'd get something that looked like that. And you get this little shape here. And if I draw in a representative cross section, it would be this here, which is a disk, right? And not that you have to do this on the AP test, especially on a multiple choice, but for note flow, we'll say, hey, what would the volume of just that disk be? We'll call it a representative disk. So it's going to be pi r squared delta, what you're perpendicular to. So it's going to be delta y, and the radius goes from the axis to the curve. So it's touching this curve, and it has to be in terms of y. So it's y squared. Remember, everything's in terms of y here. So that's the volume of one disk, but we're not interested in that. We're interested in adding up all of the disks as the thicknesses go to 0. That is the process of integration. So volume equals, I would pull the pi out of the integral from, you're starting at 0 and you're ending at this value, which was y equaled 2, right? So from 0 to 2, and y squared is y to the 4th, so spruce it, and that's it. And so now simple power rule here, you get pi times 1/5 y to the 5th, which I'm just going to go straight for it and write that. That's my antiderivative evaluated from 0 to 2. Pull out the pi over 5, 2 to the 5th minus 0 to the 5th. You end up getting 32 pi over 5. So that one actually cleaned up pretty easily. That's choice A. And there you have it. All right, so a pretty simple problem. Again, has to be done without a calculator. Takeaway here is if you're revolving around the y-axis and you're using disks, then everyone's got to be in terms of y, including your limits. All right, including your limits. Good? All righty. All right, let's move it along. 24. All right, so 24 is a little bit of an annoying question. but we'll do it. All right, so I'm going to write what they have here. So you have 1/50th radical 1/50th plus radical 2/50ths plus 3/50ths plus dot, 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 radical 50 over 50. And it said it's a Riemann sum approximation for. So, Riemann sum approximation, we're thinking, is it LRAM, RRAM, or MRAM? If you remember when we did those, right, we would do like summation of f of ck times delta x k, but we could do delta x if the what's it called? If the intervals were what? Duff, you remember? Uniform, yeah. So from 1 to n, where it n's the number of rectangles. So now if your delta x is the same, so in other words, if the width of all of your rectangles is the same, right? So all of these are the same. Well, then this can get pulled out. So you end up getting delta x times the summation of k equals 1 to n of f of ck, like that. All right. So in other words, all right, so then it's going to be delta x times the sum of things. That's what we have here. So we're thinking that this is our delta x, and then these are our functional values at some x value. Okay. So what x value, right? Well, think about how you would do this. I mean, it appears that delta x, according here, is 1/50th, right? So if I was integrating, right, and each delta x is 1/50th, say I started from 0, right, and I want to integrate this curve. This would be 0. This would be 1/50th. This would be 2/50ths, and so on and so forth until I got to, looks like in this case, 50/50ths, which last time I checked, that's 1. Okay. Now notice I started at 1/50th, right? Well, that might be because I'm doing a Riemann sum approximation where the height of that first rectangle is right there. And then the height of this next rectangle is right there, and so on and so forth until the height of that last one is right there. So think about it. My integral now looks like it's going to be from 0 to 1. Right, of what my function is. So now what's my function? Like if this would have been 1/50th squared, you would have thought, oh, your function was x squared. But it's not 1/50th squared. It's a square root of 1/50th. So it looks like your function's radical x dx. And that is your answer, believe it or not. So that's going to be choice. Where are you? That's going to be choice B. Okay. Kind of, I get it. I don't know if that was the greatest explanation of what I just did, but what you could do now is you can work the problem backwards. In other words, if I said, hey, give me a Riemann sum approximation, a right Riemann sum, so an RRAM. So do an RRAM on this and use n equal to 50, right? If I told you to do that, do RRAM on this with n equal to 50 and start setting it up, you're going to set exactly that up. And that might actually help you kind of reverse engineer what I just did. All right. So hopefully that helps. If it doesn't, rewind and play it again. If it still doesn't, repeat. All right. 25. So this is solid. 25, the integral of x sine of 2x dx. So there's real good news here for you. All right. The bad news is the product, right? So the integral of a product is not the product of integrals. So there's no way to do it that way. If you think about it, the only way you know how to do the integrals of products right now is a U substitution. So you might think, oh, let me try a U sub, but a U sub's not going to work because if you let U equal 2x, du is 2 dx, and you don't have enough to absorb this x. So a typical U sub here is not going to work. So what's the good news? This is no longer in your curriculum. So back in 97, it was. Now in the year we're in, 2020, it's not. So this is a BC topic. This is actually called integration by parts. You don't have to do it. If you were to see an integral like this on your test, it would have to be in what section? Yes, calculator section. All right, so that's that. So that's both solutions now for 1997. So hopefully you guys are doing this. Again, hopefully you're not stressed out. This is going to be solid review. So I promise you, if you do this, if and when you take the AP test, which that's going to be up in the air and how they administer it, but let's just operate as if they're going to, this is going to pay off. All right. At one point, if I have to do something new, I may somehow do a virtual extra help session, but that isn't going to happen at least within the next week. All right. So, and bear with me with all this stuff because I don't know how great it's going to be, but it's definitely better than nothing. All right. So again, if you have any questions on any of these, rewind. You can actually email me as well. Although doing an email math question is not, I don't know how effective it's going to be, but you certainly can email me questions. The other thing is I need to kind of see that you're doing this. And I'm going to be honest, the more important thing is here right now is that, we all stay inside and we stay alive, to be quite honest. So I'm not going to be a stickler in terms of grading all this stuff, but at the same time, I want to make sure you're doing this. So do the work. You write it on a piece of paper, on your notebook. Take a picture of your notebook, however many pictures you have to take, and then upload it into the folder that I shared with you. So you have a folder with your name on it that you have edit access to, so you can drop in anything you want to drop in. The intent is to drop in these assignments when completed. If you want to drop me a note like a Google Doc and write questions on that, and then I can respond to them that way as well. I'll check it every now and then. You can do that. Yeah, I think that's all I got. And the other thing is to access all this stuff, you got to be logged in as with your school Google account. So like the new website I have, which I'm doing just for ease of what I'm doing now. It's just making things a lot easier. You have to be logged into the school domain. So mine is msavante@g.bbpschools.org. I think yours is like first, last name, whatever it is. So if you don't, it'll say, error 403 forbidden, which basically means you don't have access to it. All right. So if you're having an issue with that, just log on as your school Gmail, not your personal Gmail. All right. So I hope all you guys are well and safe. 3 cloves of garlic a day, boost that immune system. Be good. Peace.